My name is Will Shaw, and I'd like to share with you some information about the Lidar Buoy program managed by the U.S. Department of Energy's Pacific Northwest National Laboratory. These systems are configured to support both researchers and industry in offshore wind resource characterization. A unique feature of this operation is that all data collected are available to any user at no cost. The systems are typically deployed at a given location over a full annual cycle, and thus provide valuable and still rather rare data with which to validate numerical weather prediction and other models offshore. The continuing need for these systems has been established by workshops and other stakeholder input over the last decade. In particular, the data requirements and gaps analysis for offshore renewable energy systems was a workshop that took place in 2011, was reported in 2012, that underscored the lack of metocean data to support renewable energy development offshore in the US. This workshop was a fundamental inspiration for the development of the Buoy program. And then in 2019, there was a workshop on research needs for offshore wind resource characterization. This workshop addressed both the scientific challenges, but also the observational challenges that remained and underscored the continuing need for this type of measurement system. The buoys were initially procured in 2014. They had a year-plus deployment each off the US East Coast during 2014 to 2017. In 2019, based on that experience, we replaced the lidars and validated the new ones in compliance with Carbon Trust recommended practices. Both buoys are now off California on the US West Coast, collecting data in their first deep water deployments. Just as an overview of the initial deployments off the US East Coast, those took place in Virginia, off Virginia and New Jersey. The first was in Virginia, began in December of 2014, and 17 months later, the buoy was recovered with the first complete multi-seasonal data set collected by these systems. The New Jersey deployment happened about a year later, and that buoy was deployed again for more than an annual cycle, and the data were recovered in February of 2017. There was a period of overlap in the winter of 2016 where both these buoys were simultaneously on station. The New Jersey buoy was 5 kilometers offshore, adjacent to a Bureau of Ocean Energy Management lease area, and the other buoy was off Virginia, about 42 kilometers, again adjacent to a BOEM lease area. This slide provides a list of instruments and their locations on the buoys as currently configured. Power is provided by a wind turbine and solar panels on each buoy, with a diesel generator as backup. The central instrument is a Leosphere Doppler LiDAR, hardened for marine conditions. And there are also supporting meteorological measurements that are collected to allow bulk calculations of surface fluxes and other analyses. The buoy also measures the two-dimensional wave spectrum, water temperature, and salinity at the surface, as well as vector currents to a depth of 200 meters. Prior to deployment to California, the new lidars on these buoys were validated against a reference at Woods Hole Oceanographic Institution's Air-Sea Interaction Tower, also known as the ACIT, under the supervision of DNVGL with excellent results. You can see the scatter plots for speed and direction on the right side of this figure. The correlation coefficients squared were in the neighborhood of 0.99, and it was a convincing demonstration that these systems are functioning very well indeed. The buoys are currently deployed near Morro Bay off Central California and near Humboldt County in Northern California. The northern deployment is in about 650 meters of water, and the water depth at the southern location is 1,100 meters. These are the first deep water deployments that we have undertaken with respect to these measurement systems. In addition to the standard suite of measurements, we have also taken the opportunity to test new avian tracking technology on the northern buoy as part of this deployment. This is a system known as the thermal tracker, and it is intended to operate mounted on a buoy, unattended, and to automate the monitoring of avian life, and represents a potential opportunity to substantially reduce the cost of some of the environmental measurements. We've carried out a variety of basic analyses already using these data. These are summarized in several technical reports that have been published by PNNL. These are available for download from the PNNL system. A Google search will come up with them fairly readily. We have begun some comparisons, in addition, between reanalysis data sets and the buoy winds at hub height to identify conditions that produce systematic errors in the models. The hard-to-read example in the lower right of the slide shows that near the coast, which is again about 5 kilometers off New Jersey, the MERA 2 reanalysis overestimates hub height winds when the wind is offshore. In addition, the NAR underestimates hub height winds when the winds are parallel to the coast. So this is a pointer to a couple of systematic biases that seem to be present in the way some of the models are configured, and we hope will point us toward identifying some physical parameterizations or other processes in the models that can lead to improvement for the numerical weather prediction models that are used offshore. We are also in the process of developing as yet unvalidated techniques to calculate motion-corrected turbulence kinetic energy and possibly some other turbulence variables from the LiDAR systems. An example of an initial calculation is shown in the upper right. The curve for turbulence kinetic energy in this figure is not what one would typically expect in the boundary layer. These were data collected near the ASIC tower during the validation. However, this was a period of offshore flow, and these platforms were very close to the shore, or, well, within a kilometer or two of the shore. And so it's quite possible that we're looking at some effects of internal boundary layers. In any case, we're exploring a number of ways to extract more information from these measurement systems. We are also using or looking at the buoys as potential platforms for instrumentation development. We would like to go beyond the basic suite that we have, and plus the LiDAR, to incorporate a variety of unique measurement systems that are suited to specific purposes and interests. In particular, PNNL is considering the value of an additional buoy for instrument testing and has gathered stakeholder input via a formal request for information. The primary purpose for this buoy would be to test and validate new measurement and monitoring technologies that might be developed by DoE or other organizations to support the need for meta-ocean data offshore. One example of this kind of instrument could be a system that would perhaps provide, in complement to the wind profiles, thermodynamic profiles over the depth of the boundary layer. That would be a tremendously valuable contribution, and there's no effective way to get that remotely over long periods of time from buoy-based systems. In addition, we are also working with the University at Albany to adapt a motion-compensated three-dimensional acoustic anemometer. This system will provide eddy correlation fluxes in the surface layer. It will allow us to directly investigate the behavior and the sensitivities of conventional surface layer parameterizations under a variety of oceanographic and meteorological conditions. Again, over the full spectrum of atmospheric and oceanographic conditions that occur over the course of a year or more. Analyses being carried out using the buoy data have resulted in 6 journal publications already, led by PNNL. We are proud of getting the cover on the Marine Technology Society Journal recently. And We're also engaging in an increasing number of conference presentations, and more publications are in process regarding the analysis of the data and the work going on in general in terms of developing these buoys. We are anxious for the global community actually to be using the data from the buoys, and we're very interested in collaborating with people. There are a number of ways to learn about these systems and to engage with the program. A great place to get an overview is at the website that we have just revamped at PNNL. I believe it's buoy.pnnl.gov. I forgot to put it on these slides, and so you may need to Google that, but it should crop up. That site contains a lot of information, including technical specifications for the buoy, information about and links to getting access to the data, information about deployments that have occurred in the past, analyses that are completed and underway, and some information about future plans. In addition, there is a loan program that has been put in place for the buoy, the two buoys, and depending on how things fit with DOE mission priorities, it is in fact possible to borrow the buoys, and there is in fact a mechanism in place for doing that. And again, we try to communicate the activities of the buoys and to engage potential researchers and the public through a variety of news, publications, and photos. Specifically with regard to data dissemination, all data collected by the buoys are archived and disseminated through the Data Archive and Portal, or DAP, developed as part of DOE's Atmosphere to Electrons, or A2E program. For users interested particularly in data from the California deployments, we are just publishing a data dictionary that will facilitate the use of those data. The buoy page on the DAP is provided at the bottom of this slide. That will take you directly to a description of projects that have used the buoys and links to download data rather directly. So in summary, DOE has an offshore wind resource characterization program that is intended to identify research needs for offshore wind resource evaluation, resource assessment. And the Department of Energy invests in wind resource characterization technology and demonstration projects, and in particular supports metocean data collection using validated methods. The buoys specifically are a realization of this program. They've been a major DOE investment since 2013 and have the distinction of having provided the first publicly available multi-seasonal hub height data collected in US waters. The buoys also serve to improve sighting, provide data that can improve sighting, optimize designs, improve reliability and performance, and increase safety and reduce capital and operating costs, all in the interest of advancing offshore wind energy in the US. So thank you for your attention. I would also like to thank Alicia Gorton, who is listed as the first author on this presentation. She is the project manager for the buoy deployments. She created many of the slides, and the artistic look of these is all to her credit. We also have a number of people who are contributing regularly to the buoy program, a number of atmospheric scientists, oceanographers, and environmental scientists. And these are actively engaged, and I am grateful for their contributions as well. So thank you very much for listening.